Welcome back. Today we're putting on our lab coats and playing doctor to our machine learning models. We are going to diagnose one of the most fundamental concepts you absolutely have to master: generalization error.
Okay, let's dive right into this because it's a classic and, let's be honest, a really frustrating scenario. You've built a model, the training metrics look phenomenal. You're getting like 99% accuracy, but then you deploy it into the real world and it just flops. It doesn't work. So what's going on here?
This gap between how it does in training and how it does in the real world, that's the key symptom we're looking at today. It points directly to maybe a misunderstanding of what the true goal of any machine learning model really is. Because after all, it's not just about acing the practice tests.
So, here's the crucial point. A model's success isn't measured by how well it remembers the answers it was shown during training. No. Its real value is in its ability to make accurate predictions on data it has never, ever seen before. That right there, that's the whole game. That's generalization.
So, to start our diagnosis, we need a reliable way to actually measure this generalization ability. We got to check our model's vitals, so to speak, to see how it's going to perform when it's out in the wild. And that measurement is what we call generalization error. You'll also hear it called test error a lot. They're pretty much interchangeable. This single metric is our main diagnostic tool. It gives us a really clean, objective score that tells us how well our model is actually learned the underlying patterns versus just, memorizing the training examples. Now, since we can't just wait around for future data to roll in, we have to simulate it. And we do this by holding back a chunk of our initial data, something we call the test set. The model never ever gets to see this data while it's learning. This test set becomes the final exam, and it gives us a really solid, unbiased measure of the model's true performance.
Okay, so here's where it gets really interesting. That final error score we get from our test set, it's not just one big single number. If we actually run the lab work, we find out it's a composite score. It's made up of three very distinct and fundamental parts.
And understanding these three sources of error is kind of like a doctor understanding the difference between a bacterial or a viral infection. You have to know the cause to prescribe the right treatment for your model. It's absolutely critical.
So these three components are bias, which is the error you get when your model is too simple, variance, the error from it being too complex and twitchy, and a third one, a really fascinating one, called irreducible error. That's just the unavoidable noise in the data itself. And this equation right here shows us exactly how they all come together. It's one of the most famous equations in machine learning. It basically says that the total expected error, often measured as mean squared error or MSE, is literally the sum of the squared bias plus the variance plus that irreducible error, that little sigma squared symbol. They all add up to that final number we see. Let's just spend a quick second on that last one, because it's a really cool concept. Irreducible error is just the randomness or natural static in a system. Think about it like radio static. No matter how good your radio is, you can't get rid of the static that's just part of the broadcast itself. For us, this means there's a hard limit, a noise floor, on how good any model can possibly be on a given dataset. This is so important for setting realistic expectations for any project.
Okay, so with this understanding of bias, variance, and that noise floor, we can now use our training and test errors to make a really clear diagnosis. We can now spot two of the most common problems a model can have: underfitting and overfitting. And the relationship between these two error scores, it tells us everything we need to know. If both your training error and your test error are high, your model is underfitting. But, and this is the one to watch out for, if your training error is low while your test error is high, well, you've got a classic case of overfitting on your hands.
So this chart is basically our diagnostic manual. A good fit is what we're aiming for. Both losses are low and pretty close together. Underfitting is when both are high, the model just isn't learning anything useful. And overfitting, that's the telltale sign, a super low training loss, but a sky-high test loss. That means the model has totally failed to generalize.
So when we see underfitting, high error across the board, the diagnosis is high bias. Our model is just making way too simple assumptions. It's like trying to fit a straight line to data that has a really complex curve. It's just never going to capture the true pattern.
And on the flip side, when we see overfitting, that big gap between training and test error, the diagnosis is high variance. Here, our model is too complex. It's too flexible. It's not just learning the signal, it's also memorizing all the random noise in the training data.
Let's zero in on that last condition for a second.
Because overfitting is often the trickier, more subtle problem to fix. It's the one where the model looks absolutely perfect in the lab, but just falls apart out in the field. This mathematical signature is the key. The J here just stands for our loss or error function. So when you see that J of train is way smaller than J of test, that's it. That's the smoking gun. You can be almost certain your model is overfitting. That huge gap is the big red flag we're looking for. So the natural question is, what's actually happening under the hood to create this huge performance gap? The answer really lies in the model's flexibility and what it chooses to pay attention to in the data.
Well, what's happening is that an overfit model is just too powerful for its own good. It has so much capacity that it doesn't just learn the general trend, it hugs every single point tightly, perfectly memorizing the training set, including all the random, meaningless wiggles and fluctuations. But of course, that very specific noise doesn't exist in the test set, so its performance just plummets. And this extreme sensitivity to the training data, that is exactly what we mean by high variance. If we were to train the same exact model on a slightly different sample of data from the same source, its predictions would change all over the place. It's unstable because it's chasing noise instead of the actual signal.
And this leads us to the central challenge, really the fundamental trade-off in all of supervised machine learning. We have to find that sweet spot. We need a model that's complex enough to capture the real pattern, which reduces bias, but not so complex that it starts memorizing noise, which would increase variance.
And that is the million-dollar question, isn't it? As we make our model more complex to drive down bias, we almost always end up cranking up its variance. It's like a seesaw. So how do we manage this balancing act? How do we find that sweet spot? Well, we'll explore the techniques for navigating this exact trade-off in our next explainer. See you then.